name is Isabella Faciano, and this is Lab 3, Magnetic Field of a Bar Magnet, for Physics 2212 at Georgia Tech. The purpose of conducting this experiment is to determine how the magnetic dipole moment of a bar magnet depends on distance. The fundamental physics principles that govern this lab are using the Biot-Savart law to calculate the magnetic field of the magnet both on and off axis, using the equation below where B is the magnetic field, mu naught over 4 pi is a constant, mu is the magnetic moment, and r is your radius vector, and r hat is the unit vector. The distance-dependent equation is also used that quantifies how the magnetic field varies with distance, where the magnitude of the magnetic field of the bar magnet is equal to k times r to the n power, where k is a combination of constants and n quantifies distance dependence. Ultimately, we got that the magnetic moment of the magnet is 7.345 amperes times meter squared, and n is negative 10.4. Some assumptions that we had to use to calculate magnetic moment were that no external magnetic fields are acting on the magnet that were not already accounted for, there's no interference with the bar magnet's field, and that the bar acts identical to a magnetic dipole. When conducting the experiment, we defined the system as the bar magnet, the surroundings as everything else in the room, and the initial conditions as the bar magnet with the phone aligned north next to it with the magnetometer app open. Setting up our experiment, we first had to initialize the magnetometer app to where it was lined up with the north magnet by getting the x component of the magnetic field as close to 0 as possible. We then placed the magnet at the end of the east-west oriented meter stick that was previously laid out. We then slid the phone perpendicular to the meter stick until the x component of the magnetic field is maximized and the y component is minimized. We then rotated the phone so it's parallel to the meter stick and moved it until the y component of the magnetic field is maximized and the x component is minimized. We chose to represent the bar magnet as a magnetic dipole because the bar magnet has a distinct negative and positive end. Magnetic field goes from the south end into the north end, like a electronic dipole where the electric field goes into the negative end and out of the positive end. Here's our data from this experiment. Below is a graph of the natural log of the magnetic field plotted against the natural log of distance. This graph was found by recording observed distances where given magnitudes of magnetic field occurred. The final line of the equation of best fit is given above, where y is equal to negative 0.0556x minus 10.4, where the y-intercept is equal to n. Below is a glow script model of the data that we collected and this experiment in general. The cyan arrows represent the magnetic field from the perpendicular when it was perpendicular, and it is pointing in the negative x hat direction. The orange arrows represent the parallel magnetic fields, which is in the positive x hat direction, and the magenta arrow represents the off-axis magnetic field, which is shown to have both x and y components. GlowScript was used to computationally calculate the magnetic fields at different locations, both on and off axis, and doing that is shown below with pictures of my GlowScript code. This computational model shown previously in the GlowScript can now be compared to our observed results recorded in lab. As previously stated, our measured magnetic dipole moment was 7.345 amperes times meter squared, and n was negative 10.4. Some differences between our models and the actual results. Using GlowScript, we found that the magnitude of the net magnetic field off-axis was 1.706 times 10 to the negative 4, but compared to the results that we found in lab, we found that the net magnetic field off-axis is 4.4 times 10 to the negative 6 Tesla. This is a 72.4% error, which is a pretty big discrepancy. Some possible sources of error that could be responsible for this discrepancy are that there may have been outside magnetic fields besides the Earth and the magnet. The phone might not have been held in the exact same place each trial, and that the distances may not have always been recorded super precisely. Some further questions that may be asked after conducting this lab are, what if the magnet wasn't oriented to compensate for the magnetic north prior to starting this experiment? All of our measurements would be skewed by some constant amount caused by the Earth's magnetic field. The magnetic field of the Earth would have to be accounted for after data collection, which would make it a lot more complicated than doing it in the beginning. Lastly, what if you were to stick two identical magnets together end to end and conduct the rest of the experiment normally? Assuming that they have the same magnetic moment, our measurements would approximately double due to superposition, but it would remain in the same direction since the net magnetic field due to the dipoles would remain the same.